A material's ability to return to its original shape after the deformation is known as elasticity. And the spring is a mechanical component that produces force when it is deformed. If you recall, the spring constant, which is also known as stiffness, the stiffness of a spring, is equal to the ratio of applied force to the deflection or the deformation. What is the meaning of stiffness? The stiffness represents the resistance of a structure to deformation as a response to an applied load. And the inverse of the stiffness is known as the compliance. Compliance is a measure of a structure's softness. The softness of a structure can be represented by the compliance. And in solid mechanics, we have studied the deflection due to an axial load and also deflection, which is the angular displacement actually, the angular displacement due to an applied torque. For example, here, let me use a laser pointer. So as you can see, so this delta represents the axial deflection due to an applied axial force F, and theta here represents the angular displacement, the rotational displacement due to an applied external torque. And naturally, when we apply an external torque, this will create some internal torque in the structure, and we can calculate the angle of rotation or the angle of twist or the angular displacement. All of them have the similar meaning by using this equation, TL over JG or GJ. T is the applied torque, L represents the length of the structure, G is the shear modulus, and J is the polar moment of inertia. And then we would like to calculate the axial deflection. Then we use this equation. F is the tensile force or the compressive force depending on its direction. L is the length of the structure. A is the corresponding cross-sectional area of the structure. And E represents the E modulus or modulus of elasticity or Young's modulus. And we also know that the ratio of force to the deflection or deformation is known as the stiffness of the structure. This can be for an axial force, or this torsional stiffness can be represented by the ratio of applied torque to the angular displacement. Probably you already know the torsional stiffness. This is relatively new. We know the stiffness of a structure due to an applied axial force here, or related to an axial force. The stiffness of a structure can be calculated by dividing the applied force by the deformation of the structure. However, if we have a torsionally loaded structure, we can measure its stiffness or calculate its stiffness as a ratio of applied torque to the angular displacement. K here, in the second equation here, represents the torsional stiffness of a structure, and here T is the torque, theta represents the angular displacement. So therefore, when we substitute, for example, for the first equation, when we substitute delta, the corresponding delta, into the first equation, we obtain the stiffness of a structure which is subject to an axial loading, or if the structure is axial loading, what would be the stiffness of the structure that we should take into consideration? Naturally, this is the axially loaded stiffness. Again, the axially loaded stiffness should be taken into consideration for axial loads or axial forces. However, the torsional stiffness should be taken into consideration for torsionally loaded structure. If a structure is subjected to a torsional load, then in this case, the type of the stiffness that we need to analyze is a torsional stiffness. And how we can calculate the torsional stiffness? The ratio of applied torque to the angular displacement, it is very similar. And we can replace the angular displacement by TL over GJ. And here, as you can see, here we obtain the torsional stiffness of a structure which is subjected to a torsion. and the first one is the stiffness of a structure which is axially loaded. Key point. Torsional stiffness is the ratio of twisting moment T to rotational displacement. The curvature of a beam, which is subject to a bending moment, can be determined by using this following formula. Rho represents the radius of curvature, m represents the bending moment, E is the modulus of elasticity, I is the moment of inertia. From math, we also know that 1 over rho can be expressed mathematically by using the following formula, and y represents the deflection here, which is a function of x, and since our beams usually subject to small deformations, the slope of the beam would be approximately equal to 0 and it would be very small. How can we determine the slope of a beam at any point along the length of the beam? By using the following formula. Theta represents the slope of the beam, and it can be determined by taking the first order derivative of deflection y with respect to x. So as you can see, the slope is equal to the first order derivative of deflection y with respect to x. And again, as I stated before, since the beam experiences small deformation, and when these theta values are very small, which are approximately equal to 0, this dy dx would be equal to 0. Therefore, the denominator of this equation here approaches unity, and therefore the inverse of the radius of curvature would be equal to the second order derivative of deflection with respect to time, and the inverse of the radius of curvature is also equal to m over ei, which means that when we combine these two equations, we obtain the following equation for beams with small slopes, which means that the second order derivative of deflection with respect to x would be equal to m over ei. The shear force function is the first order derivative of the bending moment function. Here V represents the shear force. And the first order derivative of shear force function with respect to x is actually the second order derivative of the bending moment function with respect to x, and it is equal to the load intensity function Q. So these are known, these concepts are known because these concepts were analyzed in solid mechanics. So this means that since m over ei is equal to the second order derivative of this displacement or the deflection function with respect to x, v over ei would be equal to the third order derivative of deflection with respect to x, because please pay attention to this one. The shear force function is first order derivative of the bending moment function with respect to x. So we combine them together. And similarly, q over ei would be equal to the fourth order derivative of deflection function with respect to x. Because please note that the q is first order derivative of shear force and the second order derivative of bending moment with respect to x. So this is the reason why q over ei is the fourth order derivative of deflection function with respect to x. In this example, we have a simply supported beam which is subjected to distributed loading with a load intensity function of W. When we would like to analyze this problem, for example, if you would like to determine the deflection function of this beam, first we draw the free body diagram, determine the support reactions, plot the shear force diagram, construct the shear force function, and since the first order derivative of bending moment function is the shear force, in other words, the integral of shear force function is the bending moment, we can also plot the bending moment function as follows. And please recall from the previous slide, q over ei is the fourth order derivative of deflection function with respect to x. Q represents a load intensity function. Here we have W, and on the previous slide, Q represents a load intensity function. And when we integrate this expression, when we integrate the load intensity function, actually we obtain the shear force, because the load intensity function is first order derivative of shear force with respect to x. And again, from the previous slide, please recall that V over EI is the third order derivative of deflection function. M over EI is the second order derivative of deflection function. And the slope is first order derivative of the deflection function, and at the end we obtain the deflection function. So you can proceed here by starting from the load intensity function. By integrating these expressions, we can find the deflection function, and here we see the graphical representation for each of these corresponding functions. Now let's analyze the same problem. We have a simply supported beam, its length is 20. And our main objective here in this problem is to determine the slope and deflection of this beam, the slopes at the ends, and the maximum deflection. You can easily determine the moment function here as a function of x. It is also provided in the problem statement, but it is easy to determine since we know the distributed load intensity function here, w. For this reason, we can easily construct the moment function. So this is our moment function. Our first objective is to obtain the deflection function. We will start with this basic equation. We know that the second order derivative of deflection function with respect to x is equal to m over ei. And when we take the integral of this expression, we obtain the first equation, which is the first order derivative of deflection function with respect to x. But please recall that we need to include this integration constant c1. And then when we take the integral of first equation, we obtain the deflection function, which is represented by y, and we obtain the second equation. But naturally, we need to also include the second integration constant c2. C1 and C2 integration constants are obtained by applying the boundary conditions. We know that this beam is simply supported, therefore the end deflections must be equal to 0. When x is equal to 0 and when x is equal to L, the deflections are equal to 0, the corresponding deflections, and we can determine these C1 and C2 constants. Let's set x equals 0, and since the deflection is equal to 0, we can immediately conclude that the C2 constant must be equal to 0. And now, as the next step, we will determine the C1 constant. We will apply the second boundary condition. When x is equal to L, the deflection must be equal to 0 again, because the beam is simply supported, the end deflection is equal to 0. And since C2 is equal to 0, we can find the C1 value, the corresponding C1 value. Yes, we obtain the C2 constant, which is equal to 0. And when we substitute x equals L, and C2 equals 0, we can obtain the C1 constant. The C1 constant is equal to negative WL to the third power divided by 24. Since we have determined the C1 and C2 constants, we have also obtained the deflection function, the y function, as presented by the third equation. And the first order derivative of deflection function gives us the slope function, dy dx, as presented here, which is expressed by the fourth equation. And our next objective is to determine the slope values at both ends of this beam when x is equal to 0 and x is equal to L. When we substitute these values, the slope at x equals 0 is equal to negative WL to the third power divided by 24 EI. And the slope at the other end of this beam when x is equal to L is equal to WL to the third power divided by 24 EI. So we know that from solid mechanics, the slope at the midspan of this beam is equal to 0 because we have the maximum deflection. Please recall that if we have a simply supported beam which is subjected to a uniform distributed loading, it has the maximum deflection at the midspan of this beam, and the slope, the corresponding slope, is equal to 0 because the slope is first order derivative of the deflection function. If the deflection is maximum, this means that the slope must be equal to 0. For this reason, you can substitute x equals L over 2 into your slope function, and as you can see, it is equal to 0 as we have earlier suspected. Now, our next objective and last objective is to determine the maximum deflection. We know that the maximum deflection occurs where dy dx is equal to 0, where the slope is equal to 0. Actually, this corresponds to the midspan of this beam when x is equal to L over 2. When we substitute x equals L over 2 into our deflection function, we obtain the maximum value of the deflection of this beam as presented here. The maximum deflection is equal to negative 5w, 5 times w times L to the 4th power divided by 384 EI. We can determine the deflection of a beam by applying different methods. And in this course, we will mainly focus on the superposition method and the Castigliano energy method. So these are the methods that you will apply in this course. Also in the exam you will receive questions related to the superposition method and the Castigliano's energy method. The finite element software can also be applied and used in order to determine deflections, and you will have a bonus assignment in which you will use a finite element software such as ANSYS in order to calculate the deflection of this beam. But in the exam, your main focus will be on the superposition method and also the Castigliano's energy method. These methods are the two basic and fundamental methods which are frequently used in order to determine the deflections of the beams. The process of superposition involves calculating the individual impacts of each load and then summing the results in an algebraic manner in order to determine the total effect of combined loading on a structure. However, we can apply the superposition method as long as the following conditions are met. The first condition: every effect is directly proportional to the load that causes it. The second condition: no load creates a condition that influences the outcome of another load. And the third condition: the deformations resulting from any specific load are not large enough to change the geometric relationships between the structural system's component parts. In this example, we will apply the superposition method in order to determine the deflection equations. For this purpose, we will first analyze the impact of this transverse load F, and then analyze the impact of this distributed loading. We will analyze these impacts separately and then combine them together in order to determine the total deflection of this beam. So here, as presented, so this is the impact of the transverse load, and the related equations are provided here on the left side. We have for the first part of this problem, which is related to this transverse load, we have a simply supported overhanging beam, isn't it? And for the second part of this problem, we have a simply supported beam which is subjected to uniform loading. So first we determine the support reactions related to the first part and second part, construct the bending moment equation. After constructing the bending moment equation, you can determine the deflection equations by applying the methods that we analyzed on the previous slide and also in solid mechanics. You know how to determine the deflection equation when you know the moment function. So the deflection equation of the AB part is presented here. So this is the deflection equation of the BC part, and the deflection at C point when we substitute x equals L takes the following form. So this is the impact of this transverse load. These deflections are due to this transverse load. Now let's analyze the impact of this distributed loading. We determine the support reactions, construct the moment function. After the construction of moment function, we can easily determine the deflection equation for this distributed loading. And we know that the maximum deflection occurs at the midspan of this section. After that, we will combine these two effects, the deflection produced by this transverse load and the deflection produced by this distributed loading together. We will find the sum of these deflections, and after combining these deflection functions, you can determine the deflection at a specific point, for example at the C point, at the end of this beam. You can also refer to table A9. Table A9 provides the deflection equations for different kinds of load functions, load configurations. You can refer to table A9, find the deflection equations separately for these corresponding load configurations, and then combine them together. Let's analyze the effect of distributed loading more in detail. This is our slope function. We know that this was obtained on the previous slide, and you know how to obtain the slope function for this distributed loading. But please note that this distributed loading exists only between A and B. Between B and C, we don't have any distributed loading. For this reason, the slope of this beam at B is equal to the slope of this beam at C. For this reason, if you would like to calculate the deflection of this beam at any point between B and C, we would use this following equation. YBC would be equal to theta B, the slope of this beam at B, multiplied by x minus L. So for this purpose, let's calculate the slope of this beam at point B, which is represented by theta B. Theta B represents the slope of this beam at point B due to this distributed loading, which is equal to WL to the third power divided by 24 EI. And we know that the slope in the BC region is equal to this because there is no distributed loading. And if you would like to calculate the deflection in region B due to this distributed loading, we need to multiply this slope theta B by x minus L. And after that, we will add this deflection to the deflection produced by the transverse load F by applying the superposition method. So here, the deflection function in the BC part, when we combine these two impacts together, these two effects together, the deflection of this beam in the BC part can be expressed as follows. The first part is due to distributed loading, and the second part is due to this transverse force F. The strain energy is produced when an elastic member experiences an external force that causes it to deform. The strain energy is equal to the product of the average force and the deflection when the elastic member is deformed by an amount of y. The force deflection relationship is linear, and it can be presented as in this figure. The strain energy corresponds to the area under this force versus deflection diagram. We can calculate the strain energy as follows. The strain energy, which is represented by U, is equal to F squared divided by 2K, and K is the slope of this straight line as presented in this. Yes, the strain energy, which is represented by U, is equal to the square of the applied force divided by 2K, which represents the stiffness of the structure. For different load conditions and configurations, we would have different strain equations. For example, if the structure is subject to an axial loading, in this case, K is replaced by AE over L. If you recall, this is the stiffness corresponding to a structure which is subject to an axial force. In this case, the strain energy U takes the following form, both in tension and compression. And we can replace L by dx, and when we integrate this expression, we can calculate the total strain energy along the whole length of the structure, which is subjected to an axial force. This axial force can be a tensile force or a compressive force. And if the structure is subjected to a torsional loading, in this case, we substitute the corresponding torsional stiffness into this first equation. The torsional stiffness in this case would be equal to Gj over L. Please recall from the previous slides. And when we replace this K by Gj over L, the strain energy formula takes the following form. The U is equal to T squared L over 2Gj. T is the applied torque, L represents the length of the structure, G represents the modulus of rigidity or the shear modulus, and J represents the polar moment of inertia of the corresponding cross-sectional area. Again, you can replace L by dx and integrate over the whole length of the structure depending on the problem type. Strain energy due to different types of loadings can also be analyzed. Let's first focus on shear loading. We have a pure shear element here, which is subjected to a shear force. It experiences a shear strain of gamma, and we know that the gamma is equal to the ratio of delta over L, and it is also equal to the ratio of shear stress tau to G, because when the applied stress is in the proportional limit, there is a linear relationship between the shear stress tau and the shear strain gamma. So this is the shear version of the Hooke's law. The Hooke's law can be applied if the applied stress is in the proportional limit, and G is the shear modulus, as we know. We also know that the shear stiffness K, and in general the stiffness of a structure, is equal to the ratio of applied force to the deflection. And in this case, we are interested in the shear stiffness of the structure. Since the structure is subjected to a shear force, the shear stiffness is equal to the ratio of shear force F to the deflection, this displacement delta. And we also know that the strain energy in general, as we have analyzed on the previous slide, the strain energy U is equal to F squared over 2K. Now, we can replace this K by F over delta, and the delta can be replaced by FL over AG. Here, as you can see, the delta is equal to FL over AG. So when we substitute these expressions into F squared over 2K, and the K is replaced by F over delta, and the delta is replaced by FL over AG, the strain energy due to shear loading as presented in this figure can be expressed as follows. U represents the strain energy due to this shear loading, and U is equal to F squared L over 2 times AG. And again, you can replace L by dx and integrate over the entire L. And the similar expressions for the strain energy can also be obtained for the bending loading and transverse shear loading. So you can refer to your book for the bending loading. The principle is the same. We apply the same strategy. Again, the strain energy is equal to F squared over 2K. The strain energy U is equal to F squared over 2K. We just substitute, replace the K by the corresponding equivalent. For example, for the shear loading, I have presented the strain energy. You can also implement the same strategy for the bending loading. However, for the transverse shear loading, it is a little bit more complicated, the derivations. If the structure is subject to transverse shear loading, the strain energy can be expressed as follows. The strain energy U is equal to C times V squared times L over 2AG. Here C represents a constant which depends on the geometry of the cross-sectional shape. For example, the C factor, the C constant for different cross-sectional shapes are provided here. For the rectangular cross-section, circular cross-section, and for other types of cross-sections, the C factor is presented here. If you would like to calculate the strain energy for transverse shear, you can use the corresponding C factors. Now let's analyze this example. In this example, we have a cantilever beam which is subjected to an end load as presented in this figure. One end of the beam is fixed and the other end is subjected to transverse shear force. And we will determine the strain energy developed in this beam. So this is our main objective. For this purpose, we will use the following formula which was presented on the previous slide. We are analyzing the strain energy due to transverse shear. For this reason, we need to use this C constant here, the C factor. The C factor for a circular cross-sectional area is equal to 1.11, which means that we will substitute 1.11 into this equation. Now let's analyze. First, let's draw the free body diagram of this structure of this cantilevered beam. It is subjected to a shear force, and this shear force also produces a bending moment, and therefore this fixed support here, because this is a cantilevered beam, this fixed support creates a reaction moment. As you can see, this fixed support creates a reaction shear force and also a reaction moment, and this moment is equal to negative Fx. The shear force is F, and this fixed support produces a reaction force which is represented by V. It's equal in magnitude and opposite in direction, and it also produces a reaction bending moment of Fx in order to maintain the equilibrium condition. Therefore, the strain energy developed in this beam would have two components. The first component is the strain energy produced by the transverse shear, and the second one is the strain energy produced by the bending moment. So as you can see here, this is the strain energy produced by the transverse shear. C is a factor, it's a constant. For a circular cross-sectional area, it is equal to 1.11. It was provided on the table on the previous slide. The shear force is equal to F. A is the cross-sectional area, G is the shear modulus, and M represents the bending moment, which is a function of X. Fx, negative Fx, we replace M by negative Fx in order to determine the strain energy due to bending moment here. And we take the integral here from 0 to L. So this is the component of the strain energy due to bending moment, and this first one is the strain energy due to transverse shear. And the total strain energy developed in this structure is equal to sum of these two components. The first component, the first term, is the strain energy due to bending, and the second term represents the strain energy due to transverse shear. The second important method in order to analyze the deflections of structures is the Castigliane's theorem. The Castigliane's theorem is based on the strain energy. It is a special method for analyzing deflections, but it can also be applied in order to determine the unknown reaction forces in indeterminate structures. According to the Castigliane's theorem, the displacement caused by any force can be determined by taking the partial derivative of the total strain energy with respect to that force. And if we are analyzing a structure which is subjected to a moment and its displacement is rotational displacement, in this case, we need to take the partial derivative of the strain energy with respect to that moment. Key point: Castigliane's theorem is based on strain energy and taking the partial derivative of the strain energy with respect to the applied force or moment to determine the corresponding deflections. In this example, we will apply the Castigliane's theorem in order to find the maximum deflection of this cantilevered beam. Yes, in the A part, we will find the maximum deflection using the Castigliano's theorem, and both of the terms will be included when we apply the strain energy, because please recall that in the previous example, in example 4.8, we have determined the total strain energy. It consists of two components. The first component is the strain energy due to bending moment. The second component is the strain energy due to transverse shear. We will determine the maximum deflection by taking both of these components into consideration. And in the second part, in the B part, we will determine the error if the shear component is neglected. Let me read the problem statement. The cantilever of example 4.8 is a carbon steel bar 10-inch long with a 1-inch diameter, and it is loaded by a transverse shear force of 100 pounds. So here we have a shear force, its magnitude is given 100. The cantilevered beam, we have a cantilevered beam structure, and in this example our main objective is to apply the Castigliano's theorem in order to determine the maximum deflection. Yes, this is our main objective. In example 4.8, we have determined that the total strain energy of the same beam was equal to this. So this first equation represents the total strain energy of this beam due to bending and due to transverse shear. The first term here in equation 1 represents the strain energy due to bending. Please recall that we have analyzed. And the second term represents the strain energy due to transverse shear. And from this point, at this point, we will apply the Castigliano's theorem in order to determine the total deflection of this beam due to bending and the transverse shear. For this purpose, we will take the partial derivative of the total strain energy with respect to that force, and we find the maximum deflection in the direction of this applied force. As you can see, this is the derivative of the first equation. When we take the derivative of the first equation with respect to force F, we obtain the second equation, which represents the total deflection of this cantilevered beam due to applied bending moment and the transverse shear. Actually, it is the transverse shear force causing this bending moment. And then we substitute the corresponding expressions for the moment of inertia and the cross-sectional area. We have a circular cross-section. Then we substitute the values for the force, length, E modulus and the shear modulus into this equation in order to calculate the maximum deflection. The maximum deflection is equal to 0.02263 plus 0.00012. I would like to underline that this first term in the maximum deflection is the deflection due to bending, and the second term is the deflection due to transverse shear. As you can see, the transverse deflection produces smaller deflection value, and the total maximum deflection at the end of this beam is equal to 0.02275 inches. Now let's analyze the B part. In this B part, we will neglect the deflection due to transverse shear, and we will only calculate the deflection due to bending, which is 0.02263. What will be the error? If we neglect the shear part, the error would be equal to 0.53%.